Bonjour. Français, anglais, c'est qu'il y a des gens comme j'ai fait. France, anglais? Okay. So my name is Julio, Mateo, as I said, I'm working in Montpellier. And I'm going to talk about Python microscope, which is Python library for controlling microscope devices. And this has been developed over the years with quite some people, but mainly Ian Dobby, Mick Phillips, and David Miguel Susano Pinto. Mainly in the University of Oxford. And I also work in the project. So I would like to start with why do we develop this library? So first, it's free and open source. It's a Python library, so I don't know if I have to argue why Python is good. Who uses Python here? Okay, so I don't have to explain anything. So it's easy to use, it's flexible and scalable, and it's also built with the idea of providing speed. So it's easy to use. So installation is very simple. Pip install microscope, and then you can just run it. It includes simulated devices, so you can play without hardware devices connected to it. So what it provides is a number of abstract classes which represent microscope devices. So there are cameras, light sources, stages, digital I/O, filter wheels, deformable mirrors, zoom, spatial light modulators, and controllers. Controllers is a special device that assembles other devices together into a single device. You see there are controllers that control, for example, at the same time light sources and stages and so on and so forth, so they are controlled with this. You will see there are no regular microscopes. There's not a tight stage microscope thing. We don't provide support for these devices because they're complicated, the APIs are not really accessible, and we run into licensing issues to make it open source. So it's just, essentially it's a library that's mostly developed for people that build their own microscopes. And each of these abstract classes defines implementations that control a specific type of hardware. For example, under cameras, Hamamatsu cameras, that's an example for the camera device. And then, for example, Raspberry Pi cameras. And there's always a simulated device, so you can play with it. So the interface is easy and homogeneous. Like, for example, when you have a light source, you just have to import it. You make an instance of it, like, for example, in the case of this type of laser, you have to give it as a parameter the USB port where it's connected to. You can enable it, set the power, so you see the commands are easy and transparent. And the interface is homogeneous across all devices. So if you want to use a deep star laser, the code is exactly the same. The same is for cameras. All cameras have the same functions to access the different properties of the camera. And so it's we try to use across different devices an homogeneous set of functions which are, so to say, Pythonic and easy and obvious to understand. That's not always easy because different cameras call different things differently and so on and so forth. So as it is now, you can connect to, talking about the flexibility and scalability. Normally, you're going to connect the different microscope devices to a PC. But at some point, what's going to happen is that you might run out of resources. For example, if you want to connect a second camera, which is not connected through a USB, but rather through one of these acquisition PCI Express cards, and you might run out of resources. The computer might be too slow to support multiple cameras, and then you cannot do anything. That's something that will happen, for example, with Micromanager. For those who don't know, Micromanager is another software package written in Java for controlling microscopes. So what we do in Python microscopes is that all devices can be accessed through the network. So you essentially make a server of the device, and you can control it remotely in exactly the same way. Okay, so you can make a device server for one camera, a device server for another camera, and another one for all the rest of the devices. You can mix them as you want. And then you have another computer which controls, as a client, all these devices. So in practice, you can do this in one single computer. You just have to launch different servers, device servers on the same computer. The advantage of this is also that you overcome one limitation of Python, which is the GIL. For those who know, it's the global interpreter lock that will prevent you from running different processes at the same time. So if you have a very high demanding camera, if you put two cameras, things start to slow down. Okay? And putting different servers overcomes this limitation to a certain extent. And nothing prevents you to create, so to say, create distributed microscopes over the network. So you can create your own farm of microscopes. And yeah, and you can mix this with, of course, with Raspberry Pis. Why not? And 3D printer microscopes. So I talked to you about the Python microscope. That's the layer that is providing access to the hardware. Okay, that's Python code. You're not going to control your microscope using Python code. You can write scripts to control your microscope. Most of the time, you want a graphic user interface. So we have another graphic user interface, which is called Cockpit. But you can develop your own graphic user interface on top of Python microscope. Well, what is nice about Cockpit is that, well, it uses Python microscope to control devices. But I don't have time to develop on Python microscope. But essentially, it has two big advantages. One is that you run experiments as Python scripts. So one experiment design, it's a Python script that you put in a certain folder, and then it's recognized by the software. And you can develop the logic of the experiment that you want to do. It creates automatically a graphic user interface and so on and so forth. And something that is also very powerful is that it gives you a Python REPL where you can access all the functionality of the microscope and interact lively, program on the go, whatever you want to do. How do we manage speed? Well, I said already before that we can overcome the GIL by putting device servers. But there's another thing, is that computers are inherently slow and unpredictable. You can never know when something is going to be triggered. So Python microscope provides the possibility to make devices triggerable by hardware triggers. So what Cockpit is doing, that's not done by Python microscope. What Cockpit is doing is to create an actions table. Essentially, it's going to create, at this time, you trigger this camera, and then 1 millisecond, 1 microsecond after, you trigger the laser, and then you create that upfront. And then whenever you're ready, that table is ready, you just send this to what we call an executor, and that will trigger all the devices in a synchronous way. So essentially what we're doing is having this kind of pattern where we have the general purpose PC, the PC do all the slow stuff, and then we can deploy all the deterministic timing to an executor, and it will execute it at very high speed, essentially whatever you tell him to do. And then once it's done, cockpit will regain control, and you can do whatever you want. So we combine the best of both worlds, essentially the flexibility of a general purpose PC and the perfect timing that you get with a hardware trigger device. In our case, it's an FPGA. So we have two devices that serve as executors. One is a Red Pitaya. It's a low-cost FPGA. It has a good number of digital input outputs and a limited number of analog outputs. And also some National Instruments compact Rio, which is more pricey. It's a few thousand euros. Red Pitaya is 200-300 euros, so it's kind of pricey solution. The advantage of the National Instrument is that it's very good, and you can customize how many digital outputs, inputs, and how many analog inputs, outputs, with how many bits. You can really configure it as you want. And that gives us a lot of flexibility for very complex systems. But we are looking forward to have the time and resources to implement another device using a Raspberry Pi Pico and using the programmable input outputs, because that's giving us very good performance. The disadvantage of this so far is that it does not provide analog outputs. So we will have to combine this with some kind of digital to analog converter, because many of the devices we use analog inputs to be controlled at high speed. So just not as a summary, but as a conclusion of all this, why we do all this is that because essentially it opens the door for high performance intelligent computing, intelligent microscopy, smart microscopy it's called sometimes. We have an infrastructure where we can build our own microscopes and have full control in pure Python, CPython. Okay, that's important to know. It's not any Iron Python or anything. It's real CPython, the standard implementation of Python. And we essentially can do anything. We can, with a graphic user interface, we can write a little script in the repo saying, okay, now listen to every image that is arriving to the microscope, analyze it with this function that detects the position of points of interest, and whenever that happens, stop the acquisition and do something else. Okay, that's one example of things. We have full control and the full flexibility to do that. Then that's, I think, everything I want to tell you. So you can find our website, the GitHub repo with Python microscope. There is also a GitHub repo with Cockpit if you want to use it. And that's it. Thank you for attention.